How did the solar system and the objects in it form? How did life on Earth originate? These types of questions can be investigated by studying ancient rocks, but only the right kinds of ancient rocks. Because even the oldest rocks formed on Earth have experienced things like plate tectonics, weathering, and biological activity. They're not the best samples to provide answers to these questions. Meteorites, which often haven't changed for over 4.5 billion years, have been a huge source of information about our solar system and beyond. But they're not always the right rocks either. Sometimes we must go to space and get the samples we need to answer such big questions. The study of targeted material from beyond Earth started with the return of Apollo-era samples in 1969. These lunar samples continue to reveal countless things about space science, ranging from how and when the moon formed to the effects of space weathering and how it impacts space travel. Analysis of the Apollo samples were done at various places around the globe, including here at Lawrence Livermore National Laboratory, where our scientists have been involved in sample return missions from the beginning. Following the lunar missions in the 1960s and 70s, there was a pause in targeted sample collection until 2004, when NASA brought tiny particles of solar wind back to Earth during the Genesis mission. Then, in 2006, NASA's Stardust mission returned particles from a comet. Livermore scientists helped the Stardust research team discover that materials formed close to the Sun were contained in comets that formed in the outer solar system. This revelation changed scientists' understanding of solar system formation. Next, both NASA and the Japanese space agency JAXA set their sights on asteroids. JAXA returned particles of the asteroid Itokawa in 2010, and then the follow-up mission Hayabusa 2 landed over 5 grams of the pristine asteroid Ryugu in 2020. A sister mission led by NASA called OSIRIS-REx returned over 120 grams of another pristine asteroid called Bennu. These missions and their extraterrestrial payloads have provided invaluable samples to space scientists, including those at Lawrence Livermore, to study the elements and isotopes that built our solar system. Additionally, with the pristine asteroid material, we can also study unaltered organic compounds that exist beyond our planet, which likely represent the ingredients for life on Earth and potentially elsewhere. Our ability to target specific samples in space to answer big scientific questions is crucial not only for our understanding of how our solar system formed and evolved, but it is also important for understanding potentially habitable worlds beyond our planet. The connection that sample return missions have made between astronomy and laboratory science has driven our understanding of our environments, both big and small, to unimaginable levels.